Okay, we got everybody signed in?
I can't find it.
Okay. Let's start over with the frequencies and the sound, right?
Yes.
That was the one you're so technology. Yeah. Just when you ask for help, it'll work. Okay, we've been looking a couple days at trying to figure out the slope of the tangent line. Either by eyeballing it and trying to figure out what the slope is, or then more recently looking at the limit as h approaches 0 of the slope of the secant line, which happens to be change in output over change in input. Where we go from a point on the curve, x, f of x, to a point fairly close by, x plus h, f of x plus h. We just figure out the slope of that line and use that as our approximation of the slope of the tangent line. And as long as h isn't very big, that line slope should be pretty close to the slope we really want to know. And the whole idea of letting h go to 0 is not only are we not going to have h very big, we're going to look at what happens as it gets smaller and smaller and smaller. So some of the problems, we're doing this computation with a specific h. Others, we're actually doing it more in general, trying to figure out, okay, well, what is that limit as h approaches 0? But in every time, we're just looking for a slope. Change in output over change in input. How much does y change? Of course, divided by how much x changes. So where do we need to start with questions? Is that here 1? Okay. So 1, we're given a specific curve. Y equals x squared, and we're interested at the point 39. So we've got this curve, y equals x squared. We've got the point 39. And then we're going to do this slope computation at 3 different points. X equals 2.97, x equals 3.001, and x equals 3 plus h. And then look at, well, what happens as h gets close to 0. And I said we didn't have to worry about sketching the graph. So at x equals 2.97. What's y going to be if x is 2.97? Or how are we going to figure out y? Yeah, we're on this function where y is x squared, so whatever x is, y is that value squared. And so our slope here, change in y divided by the change in x. So the two y values divided by the two x values, we pull out our calculator and we figure out what we get. let's find a calculator here. So 2.97 squared minus 3 squared, which is 9. So we get negative 0.1791 over negative 0.03. And we get a slope here of 5.97. So change in y over change in x, we just do that computation. Now the computation is more complicated because the point, I mean, we have to pull out a calculator to do that computation. So then they say, okay, well, what about it? X equals 3.001. Well, if x is 3.001, what's y going to be? .001 squared. That's the curve we're talking about here. So 3.001 squared. So our slope now, change in y divided by the change in x. So the difference in the two y values divided by the difference in the two x values. It's the same x value. This is the point we're basing all the computations off of. We're moving a little bit away from it. And so we pull out our calculator here. 3.01001 squared minus 3 squared. So 0.006001 divided by 0.001. We get 6.001. Now, based on those two values, our guess, I think, would be that the slope looks to be 6. 5.97, there we're closer to 3 and we're even closer to 6 for the value of the slope. But to make sure, we're going to change what we do a little bit. Instead of picking points, specific points, x, closer and closer and closer to 3, we're going to use a more generic point. 3 plus h. And then look at what happens if h goes to 0. So even though the algebra is a little scary, in the long run, using 3 plus h is going to be more to our advantage than continuing to pick smaller and smaller, or x is closer and closer and closer to 3. So, at x equals 3 plus h, what's y going to be? That squared, 3 plus h squared. And so our slope, change in y squared minus change in x squared, or excuse me, change in y divided by change in x. So the two y values, their difference, divided by the two x values, their difference. And now we've got to work through the algebra. So let's see, 3 plus h squared. 3 plus h times 3 plus h, we get 9 plus 6h plus h squared. First terms, outside, inside, and last. Now our hope is, as we plug in h, a lot of things simplify. Do we see anything that simplifies? Well, we've got a 9 and a minus 9. So we've got 6 plus h, or excuse me, 6h plus h squared all over h. If I factor an h out of the numerator, h then times 6 plus h, I can cancel the h's, and this actually simplifies down considerably. What would you say this is then as h goes to 0? What's our limit of 6 plus h? If we've got a number close to 6 and we add something really, really, really close to 0, what's our result? It'll be 6. As h gets really close to 0, that's not going to matter. What we're going to get for that value is 6. And that kind of agrees with what we've got here. And in fact, what we have here also agrees with what we had here. For this one, x equals 2.97. H would be negative 0.03. We've moved 0.03 to the left. Well, if we plug negative 0.03 in that formula, we get 5.97. Here, we're 0.001 past 3, h is 0.001. Plug 0.001 in that formula for the slope, we get exactly the same value. These two computations are a little bit more concrete because we don't have the algebra to deal with. But if we just dig in and work with the algebra, that computation would enable us to answer this question, any question. And in fact, the question we want to answer is, okay, what happens as h gets really, really close to 0? We bring that point that we're moving really, really, really closer and closer and closer to the point that's fixed. And what's going to change from problem to problem to problem, there are really only two things that are going to change. Where are we asked to do this argument, and what's the function we're working with? Everything else about this problem is going to be the same in all the other problems. We're going to be looking at this quotient. Change in output over change in input. We're going to have a fixed point, but it's going to be a different place. It will always be on the curve, and we'll be working with different curves. So I think that addresses number 1. Now, number 3, different point, different function. And again, same thing. A specific point that's close to 2, another specific point that's close to 2. Let's just do it in general, where we're close to 2. And when we do it in general with h, hopefully some algebra simplifies so we can answer this question fairly readily. Other questions? Should probably run through at least another one. Yes? 25? Okay, I didn't actually get to that. We'll come back to 25 in a little bit. Other questions? 15? So 15, the directions are here. So for each problem, each function in these problems, perform steps A through D. Calculate the slope of the secant line and simplify. Determine the limit. Figure out what it is at a specific point, and then find an equation of the line tangent at that specific point. So in 15, we've got a different function. In 15, our function is f of x equals 3x minus 7. Now here they don't tell us the specific point we're doing it at, but they still ask us to compute this slope of the secant line. So the slope of the secant line is f of x plus h minus f of x all over h. So still, change in output over change in input. And the change in input, x plus h minus x, they've already simplified that. That's why it's just h in the denominator. They've already simplified the change in the input. So we need to figure out, well, what's f of x plus h? Well, our function says f gives us 3 times our input minus 7. So the fact that the input's more complicated doesn't change what f does. It's 3 times the input minus 7. F of x, 3 times the input minus 7. Our hope is this simplifies, because they want us to calculate it and simplify. Well, let's see, if I distribute through, I get 3x plus 3h minus 7 minus the quantity 3x minus 7. Do we see any simplification? Let's see, I've got a 3x, and a little bit later a minus 3x. That's going to go away. Got a minus 7, minus another minus 7. That goes away. The 3h does not. So that's 3h in the numerator, h in the denominator. Does that simplify? There's a common h we can cancel. That simplifies to 3. Now, this particular one's a little unusual. Most of the time, if we do this computation at a generic point x is still going to be in the formula. But in this case, we get the slope of the secant line is 3, and in fact, most of the time, h is going to be in the formula as well. B asks, what happens as h goes to 0? Well, we don't see h in here at all. The limit as h goes to 0 is still 3. And what's different about this particular problem, we started with a line. What was the slope of this line? 3. You pick any 2 points on that line, the slope connecting them is going to be 3. Doesn't matter what 2 points you pick. Doesn't matter that the points are close and you're going to make them closer and closer. If they're on the line, the slope is 3. So even when we work through this, doing our limit and everything, the limit is still 3. The slope is still 3. Doesn't matter where we are. So in terms of C, when we look at the slope of the tangent line at x equals 2, doesn't really matter, in this case, where we are. The slope is always 3. And then the final step. What's the equation of the tangent line? Well, it's going to go through the point 2f of 2. That's where they've asked us to find the equation. What's f of 2 here? We plug 2 in, the function value is minus 1. So we have a point on the line, we have its slope, we should be able to figure out the equation. Y equals b plus mx is our general form. We've got a point on the line, 2, negative 1. So we plug that in, we plug the slope in, we can solve for b. b is negative 7. So our tangent line in this case actually ends up being the same line we started with. Because again, this was a line. No matter where we are on this line, the slope of the tangent line is always the same. for a line, it really doesn't make any sense to talk about the tangent line. The whole idea of the tangent line, what line most closely approximates the function right there? Well, the function is a line. That's the line that most closely approximates the function. It is the function. So we don't need to do anything else at that point. Now, while we've got this line, I want to talk a little bit more, because I think it leads into the question on 25. I'm at this point 2, -1. If I go to the right 1 unit, how much does y change? On a line, if we go with a run of 1, the rise is going to be whatever the slope happens to be. That's the whole idea of slope, is rise over run. So if we go over 1, we'll change whatever the slope happens to be. In this case, it's 3. For a line, we can do that computation fairly easily. Change the input by 1, the output changes by whatever the slope is. For a curve, that's a lot harder computation to do. Change the input by 1, we have to do a whole new set of calculations to figure out what the new output is. But if we knew this line that approximates our curve, a way to come up with how much does the output change if the input changes by 1 is just figure out the slope. The input changes by 1, the output changes by whatever the slope is. And so for most curves, one use of the slope of the tangent line is it's how much the output changes when the input changes by 1. And that's precisely the idea that number 25 is asking about. It poses it a different way, but that's the idea there. We've got C of x is the total cost in millions. And we're asked to interpret then C prime at 4 equals 2. So we're producing X thousand items. So in this case, we've produced 4,000 items. What C prime gives us is it is the cost to produce the next 1 in X, and since X is in thousands, it'd be the next 1,000 items. Now, we don't know what this cost function looks like. We have no idea what the cost function looks like. For that matter, we have no idea what the value, or what the cost to produce 4,000 items is. But whatever the cost is, wherever this point is, if we go over 1, the change in output is 2. That's what they told us. So if we produce another 1,000 items, the change in the output is $2 million. Things here were in millions. This is what's called the marginal cost. And that's an interpretation we're going to use for the derivative as well. C prime is the marginal cost. And what that is, it's the cost to produce the next item. Or in this case, the next 1,000 items, because X is in thousands. So rather than trying to do a computation on the cost function, which we don't even know, we're going to do the computation along the tangent line, whose slope we do know. If we go over 1 in the input along the tangent line, the output changes by however much the slope is. When we were graphing lines, that's how we plotted points. Over 1, we go up whatever the slope is. Over 1, up the slope. Over 1, up the slope. So if we go over 1 in the input, we go up $2 million. So the cost for every 1,000 we produce goes up $2 million from the point where we've already produced 4,000. They didn't tell us enough here for us to even figure out, well, how much did it cost to produce the first 4,000 items? We don't know. What we can interpret from this is to produce the next 1,000. Once we already have done 4,000, the next 1,000 would cost $2 million. So, and the idea here is we are not moving on the curve where you can figure out exactly how much it costs. This is actually an approximate cost. Too much work to figure out the exact cost. Approximately how much does it cost? Go along the tangent line. Change the input by 1. The output changes by whatever the slope is. That's about how much change we would expect in the function. Now we don't want to go very far. I mean, if our function is changing rapidly, if our function, say, was doing something like this, and we go from here way over to here, there's a huge difference between the value on the curve and the value on the tangent line. There's no point in trying to make a comparison here between what do we actually get from the function and what do we get if we go along the tangent line. But if we don't go very far, notice, yeah, there's a little difference between what we actually get the change along the curve and the change we approximate using the tangent line, but it's not a very profound difference, and it is certainly much easier along the tangent line to make that computation. Change the input by 1, the output's going to change by whatever the slope happens to be. That's a doable computation. We don't want to do that too many steps out, because certainly the function, the farther we go, the farther apart the function and the values on the tangent line are. But as long as we don't move very far from where we've built the tangent line, using the tangent line to approximate the function seems a reasonable thing to do. And in a numerical methods class, well, one could look a lot more at exactly how far off we might get. But for our purposes at this point, we are just looking for an approximation. We're not going to try to analyze how good the approximation is. There are certainly methods people have developed to do that, but we're just looking for an approximation. And so using the slope of the tangent line is a way to come up with an approximation. Okay. Other questions? Yes? 19? So 19, change the function. Our function is 8 minus 3x squared. But we're asked to do the same type of computations we did in 15. So we need to figure out f of x plus h. Well, our function is 8 minus 3 times the input squared. So when our input is x plus h, our function is still 8 minus 3 times the input squared. And then f of x is 8 minus 3 times the input squared. Yeah, our hope is that simplifies. Our hope is actually it simplifies a lot. In terms of simplifying, what should we try to do first? Well, at some point we've got to square this out. I mean, I guess we could look 8 minus 8, that's going to go away. So at some point that goes away. The x plus h squared, x squared plus 2xh plus h squared. And then minus a minus 3x squared would be plus 3x squared. So I did go ahead and take out the 8's as well. If we distribute this through, minus 3x squared minus 6xh minus 3h squared plus 3x squared all over h. Anything else simplified? We've got a minus 3x squared and a plus 3x squared. That goes away. And we've got then minus 6xh minus 3h squared all over h. Notice in the numerator there's an h in both terms. We can factor that out. And the h's cancel. So amazingly enough, what started off extremely messy simplifies down considerably. That should always be the case. Then we want to look at, okay, well, what happens limit as h approaches 0 of that? So as h gets really, really, really close to 0, the minus 3h goes away, and we just have minus 6x. And that's true whatever point we happen to be at. That's the slope of our tangent line. If we look at x equals 2, because that's what they ask us to do, at x equals 2, this slope of the tangent line then, negative 6 times 2, or negative 12. Then they ask us to come up with the equation for the tangent line at the point 2, f of 2. Let's see, f of 2. 8 minus 3 times the input squared. 8 minus 3 times 2 squared. I believe that gives us negative 4. So what we've got so far, we've got this point on the curve, 2, negative 4. Slope of our tangent line is negative 12. So we've got a point, we've got a slope. In general, y equals b plus mx. So we've plug in the y value, the slope, and the x value, we should be able to figure out the y-intercept. Negative 4 equals b minus 24, b equals 20. So our tangent line here should be this line, y equals 20 minus 12x. And notice that is a line that does go through that point. And that's the line that at that point, this original curve looks like that line. I'm going to double check that. So if we just now ask our graphing utility here to graph that original function, y equals 8 minus 3x squared. Notice we have the curve. It also goes to the point, and nearby the point, can we tell the difference between the line and the curve? Not really. After a while, yes, we can tell the difference between the line and the curve. And certainly if we were to zoom more on this, kind of the farther we go, at some point, there are definite differences between the line and the curve, but nearby the point, the line and the curve are pretty close to the same. And it's a whole lot easier to work with approximations and such using the line as opposed to the curve. If we were going to change the input by 1, so move from the point to negative 4 to the point where x equals 3. Over 1, we're going to drop 12. We should go to 3, negative 16. That's the point we get on the line, 3, negative 16. If we check that, that is the point on the line. Notice that's not exactly the point on the curve. The point on the curve is 3, 8 minus 3 times 3 squared, which turns out to be 3, negative 19. But they're still reasonably close, and it was much easier to figure out the point on the tangent line than it was the point on the curve. And again, that's the idea of the marginal cost, and other applications will have it is much easier. Let's just think, let's move along the tangent line rather than moving along the curve. As long as we don't go very far, moving along the tangent line gives us about the same output as moving along the curve. And it's easier to think moving along the tangent line. It'll be even easier to think moving along the tangent line if we can come up with a method for finding the slope of the tangent line that isn't so algebraically intensive. And that's what we're going to look at today. Is there another way to come up with this slope of the tangent line without having to go through all this algebra? Because yes, this algebra is intense, and as the functions get more complicated, it's more intense. I mean, there's a lot more work on this one than there was on 15. 15, the algebra wasn't too bad. This one, there's a little bit more algebra. Other functions, there's even more algebra. There are certainly functions we might want to think about where the algebra is just really, we can't do the algebra. So we're hoping to come up with easier ways to come up with this slope of the tangent line than always having to resort to this algebraic manipulation. So this is what we come up with out of section 2.2. That's our way to figure out the slope of the tangent line, which we also then call the derivative. And we also have some other interpretations, marginal cost. I think 2.2 even gives some other interpretations of the derivative. Okay. I want to get started in the next section because I want us to begin to see there is an easier way to do this. But I did want to spend, and we spent now a couple days on this idea, because we had just jumped to the easier way of doing this computation. I don't think we would have had any sense of why we expect that to be the slope of the tangent line. Why are we interested in that value? The ways we end up finding the derivative in the next section are much easier to apply, but they don't really tell us anything about why we want the derivative. The derivative is the slope of the tangent line, it's an instantaneous rate of change. With that. So, if you've got your homework and want to turn it in now, that's fine, or if you want to finish up and bring it by later today, that's fine as well. So we're going to be looking at 2.3. We may get into 2.4, we may not. We may just get some 2.3. 2.3 and 2.4 both have some rules for finding derivatives, and they also have some interpretations of the derivative. Today we're not going to look at any additional interpretations. We're just going to look at some rules. How do we compute derivatives? And we may or may not get into 2.4. We're just going to have to see how that works. Because so far what we've been doing in finding the derivative has been with this limit definition. Change in output over change in input. And we really haven't even used that definition. The algebra there is even more complicated than the algebra here. Here at least, in simplifying, we're looking for a common factor of h. That's usually not too bad to see. There was an h in the numerator, we could factor that out. Here we have to look for a common factor of x minus c, and that's usually a lot more complicated. So, if we're forced to use a definition, this is the one we'll use. But today we're going to move away from having to do that particular computation to come up with other ways to find our derivatives, other rules for finding our derivatives. Because we're really going to do a lot of work with functions, we need simpler rules. I mean, if we had the function, say, x to the fourth minus 3x squared plus x. With this, that would be an awful lot of algebra. It would be incredibly intense because we'd have to figure out what x plus h to the fourth is, x plus h squared. We've done that a couple times. You know, lots of things, lots of places we can make mistakes. So as the functions get more complicated, we need simpler rules to really pursue this. But this is giving us, I think, the best interpretation of what exactly is this derivative. It's a rate of change. Change in output over change in input. So in terms of our rules, the first one we're going to see actually comes from what we sort of discovered on number 15. If we have a line, the slope of the tangent line is the slope of that line. So in the case of a linear function, the derivative is just the slope of the line. And in a special case of that, if the slope of the line was 0, and so we just had f of x equals a constant, the derivative would be 0. So, if we had f of x is 6x minus 3, we should be able to interpret and compute what the derivative is. And you probably will have to turn your clicker back on and be sure to get back to the VB frequency. And our derivative here is just the slope of 6. So that's our first rule. If our function happens to be a line, the derivative is the slope of that line. And if our function happens to be just the constant, the derivative is 0. It's just a special case of that. So what if f of x is 10? What's our derivative? This is the special case. Our function is a constant. The derivative is 0. So this was not 10x. It was just 10. The derivative of a constant is 0. The next rule we call the power rule. If f of x is x to some power, and the power doesn't have to be an integer, doesn't have to be positive, the derivative is the power times x to the power minus 1. We bring the power down and we decrease the power by 1. So if we had, say, f of x is x to the 5th, what would the derivative be if we apply this rule? We bring the power down and we decrease the power by 1. So we get 5x to the 4th. What if our function is x to the minus 2? What's our derivative going to be? We bring the power down and we decrease the power by 1. Well, negative 2 minus 1 is actually negative 3. So our answer here is D. Those that said B, I understand where it came from. You just saw negative 2 minus 1 and took 1 away from 2. Well, negative 2 minus 1 is not negative 1. It's negative 3. So when we hit negatives, we've got to think a little bit more, how do we do that subtraction? But it's still the same rule. Bring the power down, x to the power decreased by 1. Might also mention, this particular function we will sometimes see as 1 over x squared. Most of the time, up to this point, we've really not liked negative powers. We prefer to write it without the negative powers. With the derivative, we actually prefer the negative powers. With the negative power, this is a much easier derivative to take than that one. There is a way we could do quotients, but it's much more complicated than just recognizing, oh, this is a negative power. We can apply the derivative that way. What about this one? F of x is the square root of x. Remember, the square root of x is x to the 1/2 power. So it is a power function. For that, we should be able to figure out what the derivative is. So we bring the power down and we decrease the power by 1. And again, the fraction in there makes the subtraction a little harder. We've got to think a little bit. 1 is 2 halves. So 1 half minus 2 halves, which is a negative 1 half. So we get here 1 half x to the negative 1 half, which was a. So, same process in all three cases. It's just if the power is negative, we've got to be more careful on how we subtract 1. If the power is a fraction, we've got to be more careful on how we subtract 1. But it's still bring the power down, decrease the power by 1. Next rule. Well, what if there's a constant multiple? So instead of just x to the 5th, it's something times x to the 5th. Or some constant times x to the negative 2nd. Or some constant here. Well, fortunately for us, if it's just a constant multiple, the derivative is the constant multiple times the derivative of the power in this case. So suppose we had this one, 7x to the 4th. What is our derivative going to be? Well, this is a constant times x to the 4th. So the derivative is still the constant times the derivative of x to the 4th. X to a power, bring the power down, subtract 1 from the power. So we get here 28 x to the 3rd, which was d. Those that said c forgot to subtract 1 from the power. So we're bringing the power down. We also then subtract 1 from the power. We get a new power that's 1 smaller, or 1 is subtracted from. So we hear 28x to the 3rd. If we are adding functions, their derivative, we just take the derivative term by term. Or if we are subtracting functions, we take those derivatives term by term, and we add or subtract accordingly. So now we can see things like the example I unfortunately erased here. F of x equals 5x cubed plus 4x squared minus 1 over x. We should be able to take the derivative of that. And we're just doing it term by term by term. That's That's what these last two rules say. If you're adding and subtracting things, give it a little bit more time. Let's see, A, B, and C were all common answers. A, B, and C all start the same way. This, much like we did here, derivative is 5 times 3x squared. This one, 4 times 2x to the 2 minus first. So we do get a 15x squared and 8x. The question is, what's going to happen to this minus 1 over x? Well, as we first see it, it doesn't really look like any of the things we've talked about so far. So the first thing we got to realize is, wait a minute, minus 1 over x could be written as x to the negative first power. Now it does look like what we've looked at. The derivative of x to the negative first power is negative 1 times x to the negative 1 minus 1. And as we watch those negatives carefully in a couple places, minus the negative 1 is plus, and x, that'll be to the negative second power. Now, none of our choices have x to the negative second, but if we convert it back then to what we typically do, we don't like negative powers, let's convert it back. That's 1 over x squared. So we actually get here b as our result, which I don't think was the most popular one. So those that said A, this is not a constant. Only the constant goes away when we take the derivative. We have to watch the negative power. And the negative powers definitely confuse the issue in a couple places. Because when we bring the power down, it is negative. So if we're subtracting a negative, that will become an addition. And when we subtract 1 from a negative, it gets more negative. Whereas if we subtract 1 from 3, the number goes down. Really, negative 2 is going down from negative 1 if you think on a number line. But in our heads, somehow we think from negative 1 we should, going down would be to 0 or something, but it's not. From negative 1, taking away 1, we get negative 2. Some more rules. The natural logarithm, its derivative is 1 over x. For the exponential, the derivative of e to the x power is e to the x power. The derivative of a to the x power, we're not going to see much because it's actually a much more complicated formula. It's the natural log of a times a to the x. Although in fact, this problem hopefully leads us to kind of understand why we call e to the x the natural exponential function. In terms of a derivative, the derivative of e to the x is e to the x. That's the easiest one. It's the most natural one for us to work with because its derivative is the easiest. All the other a to the x's, 1 to the x, well not 1, 2 to the x, 3 to the x, there's an extra factor in there as we take the derivative, so they're a lot harder to deal with. E to the x is much easier to deal with, It's the natural choice. If we're going to use exponential, let's use the base e, because the derivative just turns out so much nicer. That's more the reason why e to the x is called the natural exponential function. It just, when we're talking calculus, it's the most natural choice to use because its derivative is the most straightforward. So, we can combine this with earlier results. And so ask, okay, well, what's our derivative? Say of e to the x plus the natural log of x. So we take the derivative term by term. The derivative of e to the x is e to the x. The derivative of the natural log of x is 1 over x. And so we get b here. We do have to watch. I threw c in there. E to the x is different than x to the nth power. So we definitely have to watch as we see these. Where is x? Is it x to a constant power? That's our power rule. Is it something to the x power? Then it's one of these two. What we'll see most often is the e to the x power that we've taken the derivative of. Okay. We're not going to do the product rule now. We're going to quit here in 2-3. There is an assignment on Blackboard, but I'm going to adjust it. I'm actually going to add a few more problems from 2-3 of this type, and it will be due on Thursday. So if that assignment opened up sometime during class, so if you're looking at it now, that's going to change. I'll go to my office and change it, but there will be more problems out of 2-3 dealing with derivatives that will be due on Thursday.
Yeah. Josh, you or is he it? Yeah.
Chris, for some reason you showed back up, so can you sign back in? I don't know. Time you sign in, somebody else may show up too, but I don't know. Oh, yeah, listen, you should sign in too. Is that, you had to turn it in, right? That's the one you used?
Yes.
Okay.
Yeah, it turned off.
I don't think turning off would sign you out. I don't.
It just is temperamental.
Well, what I think happens is people accidentally hit your keystroke and commandeer your clicker and then realize, oh, my name's still up there, so
Yeah,
they
me
actually
too.
get signed in right.
Yeah.
But since they overtook your clicker for a little bit,
Kick you back off.
it kicks you off, even though they fixed theirs, you were still kicked off. It doesn't realize, oh, I can give you back.
So,
People. This is from a week ago today. I wasn't here in class.
Okay.
I was sick. I'm confused about the problem notation on emotions problems. I don't know if we went over that on last Tuesday or I'm just kind of confused what it means.
Well, I mean, it means we're taking the derivative. In our interpretation of the derivative, that's the slope of the tangent line. So, when we say x squared, that's x times x 2 times, so that there's a meaning for it. When we say f prime, that means we are taking the derivative. In 2, the way we take the derivative is we take this limit. Change in output minus change in input, or change in output over change in input.
Okay.
In 3, we're finding simpler ways to come up with the derivative.
Okay. And the h, like going closer to 0, is it always closer to, is that, well, we're always moving?
We're always moving to 0, yeah. The idea here is we've got 2 points on the curve, x, f of x, and x plus h, f of x plus h. So we moved a little bit away, and we're using another point on the curve, and we're going to bring this point closer and closer and closer. So we're always having h go to 0.
Okay.
Yeah, for our purposes, h will never go anywhere other than 0, because we're always going to bring this point closer and closer to that point.
Okay.
To try to figure out, okay, as we get closer, is there a pattern in these slopes?
Okay. Okay. So really, the prime here is just telling us that we're looking for the derivative, not that we're like.
Right. The prime is what signifies we are wanting to take the derivative.
Okay. Awesome. Yeah. That's pretty much all I was confused on. Thank you.